story about a story that has just begun.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we talk about electron configurations. So the word configuration means the arrangement of the parts of something. So in this case, an electron configuration describes the arrangement of electrons in the space around a nucleus. So basically, electrons are surrounding the nucleus, and their moving patterns are based on three main factors. The first being their energies, secondly, their orientations in space, and thirdly, their angular momentum. So we talked a little about this before. But as you study these electron configuration, you'll see that there's a pattern, and this is really easy to notice when you look at the periodic table. So first off, let's look at this one that you're all very familiar with. And you know that the elements of the periodic table are organized by numbers from 1 to 117. And the number of the element, or the atomic number, is the number of protons in the nucleus of exactly one atom of that element. But now as we study electron configuration, right here, and this is the arrangement of electrons in atoms, we see this pattern. Notice the S blocks right here and right here. And we also have the 1s2 right here. Oops. And then we also have the P block right here. And then we have the D block. And then we have the F block. And now you can notice the sequence of main energy levels. Now you can also see that these subscripts at the top right here, such as 1s1 versus 1s2, these are telling you how many electrons are in each orbital sublevel. So the pattern becomes more complex with each succeeding layer, as we kind of showed when we showed the different orbitals, whether it's an s orbital, a p orbital, a d, or an f. It becomes more complex as you go down. And they've chosen to place each element in a configuration pattern, which shows a movement into that next section. So you go from S to P, back to a larger N value, which is a higher value in energy, and now moving on to the 3P level. And so you're going to look at this going from 1s1 to 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, etc. Just snaking around in this pattern. When writing these electron configurations of atoms, we need to know a couple of principles or rules. So first off, if two electrons are paired, they basically have an opposite spin, like so, a spin up and a spin down. And now, if the two electrons are parallel, it means they have the same spin. So now I'm going to introduce to you the Pauli exclusion principle. So the first one is Pauli exclusion principle. And these are very important rules and principles that you need to know in order to draw out the different electron configurations for different elements. So this says that no more than 2 electrons per orbital. And if 2 electrons are in the same orbital, their spins must be paired. So now we talk about Hund's Rule. And don't worry, I'm going to show you how this works in a second. So now in Hund's Rule, due to electron repulsion, since electrons have negative charge, when you have 2 electrons close together, you have electric repulsion. And so electrons in the same subshell will occupy different orbitals and with a parallel spin. And this allows us to get the lowest energy. So electrons in the outermost shell are, remember, valence electrons, and these are the ones involved in forming bonds. So now let's use this Pauli exclusion principle and Hund's rule to determine the electron configuration of carbon. And so this building up principle is also called the Aufbau principle. And so basically, we're building up from the lowest energy level to the highest energy level. So let me also draw an axis right here, which is an increase in energy. So the lowest energy orbital is 1s, the one above it is 2s, and then we have 2p. You can also look at that in the periodic table that I just showed you, and you can follow it. Okay, so in the case of carbon, how many electrons does it have? It has 6 electrons. So now let's fill this out. We have 1, 2, 3, 4, and then 5, 6. It might actually be easier for me to draw out the available orbitals here for you. So remember when we talked about the s orbital, those circular orbitals, you can only fit 2 electrons max per s orbital. But in the p orbital, which remember looks like so, you have 3 orbitals, so you can fit up to a maximum of 6 electrons. So in this case, we added electrons with no more than 2 per orbital. So 2 is the max, 2 is the max in every orbital. And then using Hund's rule, if more than one orbital is in a subshell, then we add parallel spins to different orbitals, like so. So if we didn't follow Hund's rule, we would have drawn this out like so. 1, 2, 3, 4, 5, 6. But in this case, these guys are experiencing electron repulsion since they're right next to each other, and thus we want to move one of these electrons over to get parallel spins. And so this gives the lowest energy configuration, also known as the ground state. So for any element on the periodic table, basically by knowing the number of electrons that it has, you can build up using the Aufbau principle, and then we employ Hund's rule and the Pauli exclusion principle in order to build up these orbitals for each individual element.
It's